BOD analysis. Let me just share the content. Okay. Yeah, all right. So, as you can see, we have stopped somewhere here. Okay, we are talking about the dilution, right? We are talking about the dilution, and we said why dilution is important. It facilitates the dealing with high concentrations of samples, and also to avoid any errors happen while measuring the high concentrations. Okay, so these are some important points about the dilution. Okay, if you are having a problem in the camera, so that should be fine. I mean, that should be no problem. So just try. If you couldn't with the camera, it's okay. I just encourage you to open it because we can see you and we can know that you are still active with us. Okay. Here we can say, let me just put it full screen. Okay, in this slide, here if we have a 300 ml BOD bottle, okay, this is the final volume of BOD analysis, which means that if we want to analyze BOD, okay, we want to analyze BOD, we have to analyze it from a sample that has a volume of 300 ml. Okay, so the sample has to be 300 ml. If we have the volume of the sample, the initial volume was, let me say, for example, yeah, you can see here that how is the change from with the volume of sample to the range of BOD value. Now, if the volume of sample was 0.2 ml and the range of BOD value was from 50,000 to 10,000 and 500, okay, with dilution, you see how is the reduction in the BOD value range. Okay, with more value dilution, you can see how is the reduction in the value. So which one is more easy to get into that? Of course, the one with diluted. The diluted concentration is the more easy, and it is the more accurate reading in the lab. Okay, so normally when we put the samples in the lab, we dilute it first 10 times or sometimes 50 times or 100 times, and then we put it in the incubation for POD test, right? Okay, now for POD analysis, how it is run, or what happens in the BOD analysis. We agree that there are two types of bacteria. Okay, one type is called the heterotrophic, and the second type is called the autotrophic. Okay, the heterotrophic will deal or will decompose the biodegradable organics. Okay, the organic, I'm sorry, will decompose the organic carbon. Okay, the organic carbon, right? And then the this heterotrophic bacteria, the first stage, it will deal with the organic carbon in two ways. First, it will decompose third of the colloidal and dissolved organic matter, okay, to dissolve in which is the CO2 plus H2O. And the other portion, which is 2 over 3, the other portion of the organics, it will be converted to new microbial cells. Okay, so we have two products here, as you can see in the equation. We have two products. We have the CO2 plus H2O, and we have the new cells. Okay, so this is all done by the heterotrophic as at the first stage. That's what we call the carbonaceous oxygen demand. Okay, why? Because here only organic carbon is removed. We know that organic material has different elements. We have the main two elements are carbon and can be also nitrogen. Okay, so we have carbonaceous oxygen demand, and in the second stage we will have nitrogenous oxygen demand. Okay, but this one in the second stage. So in the first 5 days, for BOD, only carbonaceous oxygen demand is implemented, okay, or is conducted or is measured, okay. But if we continue after 5 days, okay, the other type of bacteria will start to be active and start its role, and this is the autotrophic bacteria. Okay, so we have two types. Heterotrophic at the 5 days, decomposing the carbonaceous oxygen demand. Okay, and the second stage after the 5 days, maybe at day number 7, maybe at day normally it's at day number 10. Okay, at day number 10, at the 10th day, the autotrophic bacteria will start decomposing the organic compounds or the nitrogen in organic compounds into nitrates. Okay, all right. So it will start to decompose the organic nitrogen. Okay, which is the ammonia nitrogen. Okay, I mean the ammonia nitrogen will start to be decomposed to nitrate. That's what we call the nitrification process. Right? So basically, the total BOD has two categories. First, the carbonaceous oxygen demand, and second, we have the nitrogenous oxygen demand. Okay? But because of the slow growth rates of the organisms that exert the nitrogenous oxygen demand, okay, so it has been assumed that no nitrogenous demand is exerted during the 5 day of BOD test. That's why we can say that the first 5 days of the BOD test is referring only to carbonaceous oxygen demand, not the nitrogenous oxygen demand. Okay? So this graph will show us the relationship between nitrification oxygen demand or nitrogenous and the carbonaceous oxygen demand. So here, this on the x-axis is the time of analyzing, of BOD analysis, and on the y-axis we have the BOD, the BOD concentration. Okay, just a minute. Okay, so as we saw just now, we have. Okay, so as we saw just now, we have the time on the x-axis, and then we have the BOD concentration on the y-axis, as you can see here. Okay. Now concentrate on this period. This period is the 5 days. Okay. As you can see here, the curve is only from the carbonaceous oxygen demand. There is no nitrogenous oxygen demand. Why? Because nitrogenous oxygen demand, or the bacteria, the autotrophic bacteria, responsible for the nitrification, okay, it will start maybe after 9 or 10 days. Okay, so we can say that BOD5 analysis is related only to carbonaceous oxygen demand. Okay, It's related only to carbonaceous oxygen demand. One might say that why don't we wait for 10 days or for 20 days? Okay, we might have more nitrogen oxygen demand in addition to the carbonaceous oxygen demand, because after that the curve is not stable, the curve is not constant. Okay, after that the curve is not constant, so you cannot have a certain indication. Okay, you will not be able to have a certain indication about the BOD result. Okay, so for the same wastewater, if you measure BOD for 10 days, if you measure it one time, two times, three times, you will find different answers. Okay? But for the same wastewater, if you measure the BOD 5 with different samples, you should have the same answer. You should have the same result. Okay? Alright. If you have any question, just raise it in the chat so that we will continue. Alright? So this curve, another photo of another shape of the curve, shows the carbonaceous oxygen demand in the phase number A, and phase number B, or curve number B, is the second stage of carbonaceous oxygen demand. Okay. Now, this curve shows something that is called the ultimate BOD. Okay. So what is the ultimate BOD? Ultimate BOD is the maximum BOD that can be exerted as carbonaceous oxygen demand, not as nitrogenous. Okay, so it's talking about only the carbonaceous oxygen demand. Now forget about the nitrification or the nitrogenous oxygen demand. Just focus on the carbonaceous oxygen demand. All right. So we have something called the ultimate BOD. So what is the ultimate BOD? Now imagine that for a human being, for any person, he has a maximum limit of eating. Okay, so if you gave him a meal, okay, or a large meal, okay, so he can eat it. He can eat it, but it might take some time. For a person, it might take 30 minutes. For another person, it might take 1 hour. For third one, it might take 5 times, 5 minutes. But at the end, it's only the large meal is the same. What I'm trying to say is that for the bacteria, for a certain type of wastewater, let us say maybe wastewater is coming from the house. Okay? So for this certain type, the bacteria has an ultimate limit of has an ultimate level of BOD. Okay, for BOD. Okay, for BOD. Analysis. Please everyone do mute the mic if you interrupt, so that I not disturb. Okay, all right. So what is the ultimate BOD? The ultimate BOD is the maximum limit. Theoretically, it is the maximum level of BOD that the bacteria can go for. Okay, carbonaceous oxygen demand, the carbonaceous bacteria, the heterotrophic bacteria. Okay, it is the maximum amount of oxygen that can be consumed by the heterotrophic bacteria. But this one is theoretical. Okay, in the lab, it is hardly or it is cannot be determined or achieved. Why? Because before achieving the maximum BOD or carbonaceous BOD, another type of bacteria will start acting and will start also consuming the dissolved oxygen, and that will cause mix between carbonaceous and also be reproduced. So that's why it's not that easy to measure it in the lab. So, but normally when we analyze BOD, we depend only on BOD file. We don't depend on the ultimate. Although the ultimate is measured, is calculated, estimated, okay? But in the lab, the measurement is only for BOD file, okay? So that is the ultimate BOD. Ultimate BOD is the maximum BOD exerted by the waste, but this value is theoretical. Is theoretical. Okay? Let me continue here. So this is the relationship between the carbonaceous oxygen demand curve and also the ultimate BOD. Okay? Simply BOD equals ultimate BOD times 1 minus 10 to the power minus kT. Okay? So the K is the reaction rate constant, the T is the time, the L node is the ultimate. Okay? So with the change of the K, there will be a change of BOD. With the change of the T, there will be a change in the BOD value. Okay? So this is the equation that relates both parameters. Now, how can we determine this value of K? Okay? BOD K rate. Now, as we said just now, different people has different ability of eating such meal. Okay, so that means that the rate is different from one to another. Okay, the rate is different from one to another. One can eat in half an hour, but another one can eat in 2 hours. Okay, another third one has to spend all the day to finish this dish, and so on. Okay, so how to determine this BOD or this K rate for such wastewater? Okay, so for each type of wastewater, the K rate will be different. How to determine? Now we have to measure the BOD. We run a same BOD analysis. We bring the incubation with a 300 ml and we put it in the incubation at 20 degrees. And then we start measuring the dissolved oxygen at every day. Day number 0, day number 1, day number 2, day number 3, day number 4, until we reach day number 5. And for each day, we measure the BOD. Okay, day number 1, we can measure the BOD because we know that BOD equals dissolved oxygen initial minus dissolved oxygen final. All is divided by the P. The P is the what? Is the dilution factor. Okay, the dilution factor. This equation have we have discussed it before. Okay, and then we come out with this term time, which is here is 1 over BOD, which is here is the attribute, all to the power 1 over 3. Okay, all to the power 1 over 3. Please mute the microphone. Please. Mute the microphone, please. Okay, I believe that you are using a handphone, but please. All right. Okay. Now, from the experiment results of BOD for various values of T, we calculate this term, as we said, it's now for each day. Okay? So, after that, draw or we plot a curve, which is this term, T over BOD to the power 1 over 3 on the y-axis, and on the x-axis we plot a T. Okay? So after that, we will get the line or the best trend line, okay, and then we can measure or we can calculate the B, which is the slope, and the intercept A. This is simple mathematics. Okay, so we calculate K. K equals 2.61 times B over A. Okay, so this is the value of K. This is the value of K. K equals 2.61 times B over A. B is the slope and A is the intercept. Okay, so now we continue. So from that curve we have the equations. Okay, we have the equation of L naught L naught equals BOD over 1 minus 10 to the power minus KT. If we want to change the base 10 to the base E, we have to convert the K capital to K small. Okay? K capital to K small. This is to change the base E and base 10. Alright? So here we have two values for the base 10 and for the base E. Okay? So those two equations relates between the L naught and the BOD test. Okay? And the BOD value. So the L naught is the maximum ultimate level that can be reached by the heterotrophic bacteria. Okay? BOD is the value after 5 days or after certain days, because here we have T. So it can be at 5 days, can be at 3 days, okay? But make sure that there is a consistency, okay, between T here and the T in the power. Okay, so if we say like BOD5, so we have to put 10 to the power minus K times 5. If we are measuring BOD3, okay, so T has to be changed to 3, alright? So it has to be consistent between the BOD and the power, okay? Alright, so let's continue. So for simple compounds, such as sugars, starches, those are easily utilized by microorganisms, which means that the K is very high. The K is higher only, okay? Because it is easy compounds to be decomposed by the bacteria, so the rate is high. Okay? If for complex materials like phenols, okay? So the K is low. Why? Because it is difficult for the bacteria to decompose, so the K is low. Okay, the K is low. As we said, for different people, they have different ability or speed in the eating, for example. Okay, all right. So now for according to the type of wastewater, we have also different K rates, different rates of K. Okay? For the tap water, you can see that the K is 0.04, while for example for the raw sewage it is much higher, which is 0.15. Okay? So can you guess why this difference between those two types of water? For the tap water is 0.04. For the raw sewage or the wastewater before treatment, it can reach up to 0.3. So can you guess why this difference? Okay, why here the K is low and why there the K is high? Can you write in the chat? Write in the chat if you have any answer. Tap water hasn't been used. Or sewage have been used. What do you mean by have been used? Different pH? I don't think the pH is the only factor. Something more significant that causes this factor, causes this difference. Is something. Okay. Now, if okay, the roosters have more organic material. Yes, correct. the raw sewage have more organic material than tap water. Okay, so there is more sufficient food, of course. Okay, more sufficient food for the bacteria in the raw sewage. So it will encourage the bacteria to act in a more rapid way. Okay, so the K will be higher. In the tap water, there is almost no organic waste. So the rate of the activity of bacteria is very low. And that's why the K is also very low. Okay, so that's why the difference between both values of K. Okay, now the K also is different according to the type of wastewater, but it is also different from temperature to another. Okay, in the warm temperatures, it is somehow higher than the cold temperatures. Why? Do you know why? Can you guess why? Why the K is higher in the warm temperatures? For example, K in Malaysia is higher than the K in Europe. At cold temperature, microorganism is not active. Correct. Correct. Because bacteria will be less active. Okay. Because on the other side, warm condition is active. Yeah, that's right. So bacteria in the warm conditions, it will be more active. Okay? In the cold temperatures, it will be less active. Okay? So how do we adjust the value of K? Okay? We have the standard values of K depending on K20 or 20 degrees. Okay? But if we are dealing with higher temperatures like 25 or 30, 35, okay? So the K has to be also different. Okay? So this equation will make an adjustment of K value according to the temperature. Okay? So KT at any temperature, which is maybe 30 or 15 or 18, okay, equals K20 times 1.47 to the power T minus 1. Okay, so don't forget to adjust the K if it is needed according to the temperature used. Alright, here are an example, fast example. DOD test was conducted on domestic wastewater at 30 degrees. Okay, notice that we are dealing now with what degree? 30 degrees, which means that we will need to adjust the K. Okay, the wastewater portion added to the DOD bottle was 20 ml. Okay, so this is the concentrated wastewater. So what about the rest of the bottle? Because we have 300, so the rest of the bottle was filled by distilled water. Okay, by distilled water. Now, the test was run, and for each day we were measuring the dissolved oxygen. So at the initial dissolved oxygen was 7.4, okay? And the final, at 5 days, the dissolved oxygen was 2.1. So we can easily measure or know the value of DOD for each day. For day number 1, DO initial minus DO final. For my day number 2, DO initial minus DO final, which is at day number 2. And at day number 3, same. Okay, now, it is required to calculate the value of DOD. Can anybody guess how much the value of DOD will be? Okay, now we will write here together before we go to the answer. Now, DOD equals DO initial minus DO final. But all of this has to be divided by the value of P. Okay? So, first of all, we have to know the value of P. Now, how much the value of P here? P equals what? P equals the original volume or the concentrated volume, which is 20, divided by the total volume. Total volume of the analysis is how much? Is 300. Okay? And that gives an answer of how much? 20 over 300 is 1 over 15. Okay, so this is the P. Now let's go to the BOD. So BOD equals BO initial is 7.4. 7.4 minus BO final at 3 days is how much? Is 3.7. 3.7. Okay, all is divided by 1 over 15. 1 over 15. Okay, so this is the equation that, or this is the calculation that has to be done. Okay, so here equals what? Equals the final value of BOD at BOD. Let us see in the solution. Okay, so first we have the BOD3 is BO initial minus BO final over P. So the P is 20 over 300. The BOD at 3 is 7.4 minus 3.7 over 20 over 100. So the final answer is 55.55. Okay. The second requirement, we want to determine the rate of K. Okay. Now, we agree that the rate of K has to be determined from the plot between time and this term. Okay, so the time will be on the x-axis, and this term will be on the y-axis. Okay, now we have the dissolved oxygen, so we can measure the BOD for each day in the same way. Okay, in the same way here, we measure BOD at day number 1, at day number 2, day number 3, day number 4, and day number 5. So we can measure this term, we can calculate this term, time over BOD over to the power 1 over 3. Okay, so we measure this term. We have the time, we have this term here, so we can plot on x-axis and y-axis. After plotting, we will have something like this. So we can, of course, we will have dots. Okay. So after plotting, we will have dots. We write it here, for example, a dot, 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 dot. Okay. Dot. And then you can draw a trend line between those dots. Okay, so the slope is calculated 0.016 and the intercept is calculated as 0.322. So on this equation we can measure the value of K30. Okay, so this is K30. Why is K30? Why it is not K20? Huh? Because from the beginning we are dealing with a 30-degree BOD. Okay, we are dealing with BOD at 30 degrees. Now, if the temperature changes, so we have to measure another value of K. Okay, if the temperature is 20, so we have to measure another value of K. So from the beginning, the K was at 30, at temperature of 30. All right. If we continue, so BOD 5 at 20 degrees, we want to measure BOD 5 at 20 degrees. This is the third requirement. Okay, notice that here we have 20 degrees, but however we measure the BOD at, we have here 20 degrees, but we have the K at 30 degrees. Okay, so how are we going to deal? We have to change from K30 to K20 first. Before using the value of K, we have to adjust it to the K20. Alright? So the K20 equals K30 over 1.047. This is the same equation we have used before. Okay? This is the same one. So a K20 we adjust using the same equation. Okay? The equation of adjustment for temperature. So after adjustment, the K20 equals 0.08 day. Alright? So similarly, we can measure also we can calculate the L node, okay, the ultimate BOD. So the ultimate BOD equals BOD over 1 minus 10 to the power minus K times 3. Now here, why we use K30? Because this BOD is measured at 30 degrees. 3 days it was measured using the temperature of 30 degrees. If we want to substitute the K20, so we have to find BOD3 at K20. So there has to be consistency between temperature and time, between the BOD and between the power here. Okay, so the BOD here, the value of the time is 3. So T here must also be 3. So the BOD also was measured at 30 degrees, so the K has to be at 30 degrees. So don't forget this consistency, okay, between both values. Alright? So the final answer is 93.7. And notice that always the L ultimate or the L naught is higher than the BOD or the original BOD value. Okay? Then, now we can measure BOD5 at 20 degrees. As we have already the L naught for this wastewater, so we can measure any type or any value of BOD. Okay, now this L naught, if we change temperature, is it going to change? If we change the temperature, for example, if we measure the BODs at 35 degree, no, 35 is very low. Maybe at 28, okay? At 28 degrees, 28 temperature, 28 Celsius. Is it going to change the L naught or the L naught will remain the same? And you just type in the chat. Is it going to change or not change? We deal with different temperature. Does it affect the L naught or not? Change because it's involved K. Okay? Change. 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 All of you saying change. While the correct answer is it will not change. It will not change. Why? Because, as I said, L naught is the ultimate level. Is the ultimate level of bacteria that can exert or carbonaceous oxygen demand. Now, the only difference is that the K will be changed, yes, but that will not change the L naught. Refer back to the equation of L naught. Okay, refer back to the equation of L naught. Let me show you just because we don't want to mix up on this point. Okay, now here's the equation. Okay. Let me see here. So here the equation of L naught, as you can see, let's see this one. So L naught equals what? Equals BOD over 1 minus 10 to the power minus KT. Now, we know that for BOD 5, let me say, okay? BOD 5, if we measure at 20 degrees, so K has to be at 20 degrees. There is a consistency between K and the value of temperature here. So here we have a temperature. Okay, example 20 degrees. Okay, and this K has to be at 20. Okay, if the BOD was measured at 30 degrees, of course it will not be the same. It will not be the same as BOD 20. Okay, let me write something here. So BOD, for example, 3 at 20 degrees does not equal to BOD 3 at 30 degrees Celsius. Okay? So when the temperature changes, the BOD will change, but the L node will not change. Because the L node is something like a feature of the wastewater, of this kind of wastewater, of this specific wastewater. Now, if I told you that the density of a material, okay, the density of the aluminum, the density of the iron, okay, whether the temperature was 20, was 30, the density is the same, because the density is something not related, is something related to the structure of this material, okay. Will not be different between temperature and the other. But maybe the elasticity will be different. Okay, at temperature 30, temperature 40, the iron becomes more elastic. Okay, you can change the shape when you heat it. Okay, but the density is the same. So same goes to the L node. L node is something related to the wastewater, the type of the wastewater, not related to temperature. What will change the temperature is the BOD, not the L node. But the L node, the maximum level is the same. Okay, as I said, as a human being, he has a maximum level of drinking like 3 liters or 4 liters of water. Okay, you can drink these liters in 3 hours, and also if you are more strong, you can drink it in 1 hour. Okay, but at the end you will not drink more than 3 liters. This is only a simple example. Okay, so that's what we mean by L naught. Don't mix up. L naught does not change with temperature. Okay, the thing which changes with temperature is the BOD only. Okay, so continuing here, we have measured the value of L naught. Okay, after that, we came to measure the BOD 5 at 20 degrees. We have L naught, so we make that calculation to measure the BOD 5 at 20 degrees. We have L naught, we have the K20, okay, we will calculate K20, so we can measure BOD 5 at 20 degrees. Same, we can measure BOD 5 at 20 degrees. Same, we can measure BOD 7 at 20 degrees. Okay, using the same L naught. Using the same L naught. It will not change. It will not change. Because the L naught is not related to temperature. L naught is related to the type of wastewater, to the structure of wastewater, to how much organic content in this wastewater. Okay? So the organic content will not change with changing of temperature. If the temperature was 30 or 20, the thing will change is the activity of bacteria, not organic content. Okay? Okay, I think I will stop at here because now it's almost 12. Okay? So on next class, whether it is maybe a replacement class or the normal class, I will discuss with you later. We will continue with the chemical oxygen demand and continue with chapter 2. Right? So for now on, if you have any question, please let me know. If you have it, okay. Here Farah is asking, they told me I asked question regarding the formula. Formula is 2.61 over BL and now what is B? Okay. B is the slope. B is the slope of the trend line. Let me just go back. So B is the slope of the trend line. Okay. So we go faster here. So B here. Okay, sorry, B is the slope. Okay, B is the slope. So the slope is determined easily using the angle here and the sine, cosine. So you know this mathematics, this basic mathematics in secondary school. So it's something to be easy. Okay. and this is the value of B. Alright? Yeah. So, okay, for now, any question? Do you have any question? If you have any question, just write it down so that we can answer it. If you don't have any question, we will end the class and we can, okay, so we'll end the class, then end the session, and we must see you maybe on next Thursday. If not on Thursday, we might make a replacement before Thursday, but I will arrange maybe. Alright? For now, any question? If you have a question, we will leave the class. So thank you so much, everyone, and thanks for attending. And I'm really sorry for this delay. I hope all of you have understand what we discussed, and next time we will start with COD and other. We continue with chapter 2. From now on, thank you so much. See you later. Assalamu alaikum warahmatullahi wabarakatuh. Have a nice day. Take care.